Hello everyone, welcome back to more fun Chem 2C stuff on chapter 11. This time we're still on galvanic cells, but we're going to be talking about the cell potential of the galvanic cells. So for cell potential, there are two different kinds of cell potential, I'd say. The first one is the standard cell potential, which is E and then E naught cell potential, which is what I'm mainly going to be talking about in this video. And then the second one is the E cell potential without the naught. And this just means this is the standard cell potential. So at, I think at equal concentration. So if both solutions are 1 molar, 1.0 molar, and it's at 25 degrees Celsius. And that's the E cell. And then the other one, factors can change it. Basically, we'll get more into that in another video. But for this, remember how earlier I said a galvanic cell, the transfer of electrons in a galvanic cell is basically electricity. And that electricity transfer can be measured, and cell potential is how we measure it. So in a galvanic cell, that is usually galvanic cells are spontaneous. And if you remember from Chem 2C or in other ones, spontaneous means that the reaction could occur on its own, that it's in favorable conditions with no other pressure on it, it'll occur. Like think about it as a hill, ball on a hill. Let me redraw. If you put the ball at the top of the hill, it's gonna go down. That's spontaneous. That's a spontaneous reaction. But if you put the ball at the bottom of the hill, it's not gonna go up. So that's the easiest way to explain spontaneity. So in a galvanic cells, this reaction is going to happen on its own if you bring all the elements together, the salt bridge, everything. And then the opposite would be if these two solutions swap places, then the cell would no longer be spontaneous, which means it won't. You have to put electricity in for this electrons to transfer instead of the other way around, where this creates electricity. All right, and this electricity is measured in units called volts, which is joules per coulombs. You can calculate each other. Do the I guess algebra to find the joules or the coulombs or the amps from the volts. Could mostly make another video talk about how to transfer the units and how. So in terms of cell potential, how it's measured is, I guess I'm not really sure how, but I guess a while ago a bunch of chemists came together and they used the half reaction. So half reaction is, so these two are, let's say these two reactions are in a galvanic cell. So zinc going to zinc being reduced to zinc 2 plus being reduced to zinc, and Fe3 plus being reduced to Fe2 plus. So these are a galvanic cell. If you write those two equations together, I'm going to show you what it looks like later on in this video, a full cell reaction. But each of them individually, they're half reactions, and when they come together, that's a full reaction. So this is a half reaction, and this half reaction was measured. You don't have to measure it because someone out there already did. Probably some chemist from a while ago already measured it, and they found out the standard potential. And keep in mind, this standard potential, usually you're going to be given it. It could be oxidation standard potential or reduction standard potential, but usually it's going to be reduction standard potential. That's why we labeled it right here as E cell reduction. This is a standard reduction potential. And right here is a table of these standard reduction potentials that you're probably going to be given in the test that contains cell potential, because you're not supposed to memorize them. They're given and you can look them up usually, because that's why other chemists did in the past. So you can just look it up and figure out how your the cell that you're making would work. And that was figured out, like I said. They did the half reaction for hydrogen, and they figured they used that as a standard. So they use that as like the baseline for 0, and then anything less, it's a negative, and anything more, it's a positive. And that's the standard reduction potential. And now let's get into what the numbers mean. So if the standard reduction potential is a negative, that means that this half reaction doesn't like to be, what I say, doesn't like to be reduced, essentially. Yeah, if the E reduction standard, if the E standard reduction is a negative, that means that this half reaction it doesn't want to be reduced. So it doesn't want to be, it would rather be in this format where zinc equals to, or use this notation instead, zinc 2 plus 2E. If you can see in this, it's getting oxidized instead because the zinc goes from a charge of 0 to a charge of 2 plus, so it's getting oxidized instead of reduced. And this zinc, so the element zinc, would rather be oxidized than reduced because the standard reduction potential is negative 0.76. And if this was a standard, what would I say, oxidation potential, then it will be positive 0.76. They're just the opposite of what the reduction is. But you don't have to know the standard oxidation reduction potential. Standard oxidation potential, because we're just going to use reduction most of the time. But I'm just saying this to get the concept down. The standard reduction is this, and if it's a negative, that means the cell, that means the element would rather be oxidized instead, which it would rather be like this. And while we would use that in this context is that, as you can see, the other half reaction is a positive. The reduction is a positive, which means it wants to be reduced. And why I wrote this down here is this is a common theme. As you can see, the zinc is in the anode while the iron is in the cathode, which means that this, what do you call it, the thing that, I forgot it's a word, the thing that a saying that helps you remember stuff better. Red cat and ox. Red cat means reduction cathode, so reduction usually happens in cathode, and anox means oxidation usually happens in the anode. Anode, oxidation. And right here, this diagram is proof of that, as this zinc would rather be oxidized, so that's why it's in the anode, while the iron would rather be reduced because it has a positive reduction potential. That's why it's in the cathode. So like I told you at the start of the video, I'm going to be writing a full reaction. These are half reactions, and then the full reaction for this would be you combine these two equations together. And how would you do that? Well, you have to flip one of them. And since this one's the negative one, I told you it would rather be oxidized, like it would rather be in this form. Zinc goes to zinc 2 plus 2E. And then the E oxidation becomes positive 0.76. The zinc would rather be in this form because it's negative, so you want both of them to be positives. The E potentials, so that means you have to flip this to E oxidation instead of E reduction. And now the other one would remain the same since the reduction is positive. Since we're writing a full reaction, Fe3 plus E. And also we're flipping this as well because we want the E's to cancel. In order to get, we can't have a reaction with electrons in it, so we have to get the E's to cancel. And as you can see here, on this side has 2 E's, while this side has only 1 E. And how we do that is we have to put them with the same coefficient. So we have to have this side have 2 E as well in order to cancel it out. And what we'll do is we multiply the whole equation by 2. And when we do that, the E reduction, the standard reduction, remember earlier it was 0.771. Instead of, since we're multiplying the whole equation by 2, instead of a trick, there's something that most people think is that the reduction potential also gets multiplied by 2, but that's wrong. The standard reduction potential never, so even if you multiply this times 1,000, it's still 0.0771 volts. That the standard E cell, so this never changes. It's always going to be one of these values. Whatever value is here, it's always going to be that regardless of the coefficients or the molarity. But the other E value I was talking about earlier that I could talk about in another video does change, but we'll get into that later. Anyways, in this problem, the E cell, the E reduction right here is still 0.771, even though we're multiplying it by 2. And we're doing that just so the equation can cancel out. And when we multiply it by 2, this becomes 2Fe plus 2 electrons plus 2Fe2 plus. And now we can cancel out both electrons. Two electrons cancel out since this is the product and this is a reactant. We can cancel it out since it's on either side. And the full reaction becomes zinc. I'm not gonna, usually you should add like solid what phase it is, but due to lack of space, I'm not gonna do that. And then it'll be the products. So put the reactants, zinc plus 2Fe3 plus becomes, now we go to the products, zinc 2 plus F2Fe, 2Fe2 plus. And now this is the full reaction of both of them combined. And in order to get the standard the E potential for this time when we write the E, it's not going to be a reduction potential, it's just going to be an E cell, since it's a full reaction now. One side, so over here, the zinc is getting oxidized because it goes from charge of 0 to a charge of 2 plus. So zinc is getting oxidized while Fe goes from a charge of 3 plus to a charge of 2 plus. So Fe iron is getting reduced. So the E cell, it will just be E cell instead of just E oxidation or E reduction. But then, since you're adding both equations, you have to add the E cells as well to give you the total E cell for the full reaction. And when you add these, you have to use a calculator. 0.76 plus 0.771. The total E cell would be 1.531. And remember how I talked about spontaneity at the start? If the standard E cell is positive, that means that this reaction is spontaneous and it would produce electricity and it would carry out on its own. So spontaneous. And another thing to know is when it comes to this is the easy way, instead of writing, so let's say you're asking a question, you're given these two values, you're given, let me highlight it, you're given these values and you're told to find the total potential for the cell. So you're told to find this E cell. Instead of having to write out the full reaction, there's a formula for like a sort of shortcut that you can take, and the formula is the E of the I think it's E cathode, E cell is equal to the reduction, standard reduction. So it's reduction, by the way. Let me label that as well. Standard reduction potential of the cathode minus the standard reduction potential of the anode. And this formula is essentially saying what I just explained earlier about how the anode is the one with less the E value, the E reduction with less than this, so the negative one, or it doesn't even have to be negative. This one, as long as it's less than this, so as long as 0.76 is less than 0.771, this is going to be oxidized. So we're going to use the oxidizing, so we're going to have to flip the signs. And it's the same thing if you go in this formula, because the E reduction, the E standard reduction of the anode, the negative is going to make it flip signs anyways. And I'm going to plug these numbers in to prove it. So over here, E cell, if we use the formulas here, the reduction potential of the cathode, remember I told you whatever is getting reduced is the cathode and the oxidation is the anode. If you look at these two numbers, the iron, this one, has the higher E reduction value. So that means it's more likely to be reduced. It wants to be reduced more. While this one has a lower E reduction value, which means it wants to be oxidized, which means it will be the anode, while this one would be the cathode. And cathode, and down here it's going to be cathode minus anode. So we use the reduction potential of the iron first, since it's the cathode, so it'll be 0.771 volts minus the standard reduction potential of the anode, which is the zinc, because it's getting reduced again, minus negative 0.76 volts. And if you plug this into a calculator, the minus becomes a positive. So it becomes the same thing like we did before, 0.771 volts plus 0.76 volts, and we get the same answer over here, which is 1.531 volts. And that is how you do the standard. I'm gonna write it down here. This video is mostly focused on the standard cell potential and its calculations.